We will get started with our BrainX Community Live event today, July 2024. Thank you all for joining us for this another exciting summer event. We have some excellent speakers and some excellent work that we wanted to showcase through this session. So for those who are joining us for the first time, BrainX Community is a community that we formed, which is for machine learning or AI in healthcare for good. We have had 6+ very successful years. We have now grown to be 6,000 plus member international community, which is very multidisciplinary, featuring people from different backgrounds, machine learning, AI, clinicians, investors, company leaders who are interested in AI in healthcare. A very strong LinkedIn group with 3,000 plus members. So please join our LinkedIn group with the same name, BrainX Community, where we share a lot of scientific information, and that is available to you, and a lot of discussion that takes place over there too. All the resources are available to you through brainxai.org, and I'll show you some of the features of our webpage. And we do these monthly live sessions to bring us all together and feature some of the prominent work that is being done around AI in healthcare so that our patients and our clinicians can benefit from that. This is our website. It provides you with a unified platform for AI and healthcare resources. There are a few different sections. The Connect section, which has all the information about our prior events or upcoming events. So even if you miss something, you can go to our Connect segment and you can watch those through our YouTube channel. As I mentioned, we have our YouTube channel, so please subscribe to that so that as soon as we upload the videos of any of the events, or now we have even gotten our podcast featured over there, you can get those delivered right to your mailbox or your notification. As I said, a very active LinkedIn group. We share a lot of scientific information, opportunities to meet together, opportunities to collaborate. So please join us there on LinkedIn and share your work and share the opportunities to collaborate. Learn section on BrainX Community provides you with a curated list of articles, journals, books, and courses. Of course, we can't provide you the articles directly, but we provide links to these articles. These are the latest and the greatest publications everybody's talking about, and feature some of the prominent work by prominent researchers from across the world. You can filter them for what you're looking for, either healthcare specialty, and recently also LLMs or generative AI. And everybody's looking for data too. So you want to get access to open source data sets. We have the largest repository of links to open source data sets. Again, you can filter it based on your subspecialty of choice. And we have included large language models in there too. So if you're looking for large language model related data sets, you will be able to access that through our data section too. Our very prominent podcast series, which features experts from across the world who are working on AI in healthcare, and their journey, their stories, their inspiration, their work, and their vision for the future, all is available through the podcast. And you can subscribe it through any of your podcast mediums. It can be Spotify, Apple, or YouTube. So you can subscribe to the podcast and get to listen to these experts. And conferences, you're all looking for conferences so that we can all connect, interact, showcase your work. They're all listed featuring AI in healthcare conferences so that we can connect and hopefully meet there in person too. A lot of frameworks and tools. This is Humanly, the human evaluation of large language model. How do you do that? So a lot of frameworks and tools also available through our website. That brings us to today's event, which is focusing on pathology. And it's interesting, we every year provide this year in review, looking at publications for AI and healthcare for last few years. And of course, radiology or imaging has been the front runner related to that. But you can see pathology is right there after imaging or radiology. And it is a very exciting time. So many foundation models or generative AI solutions that are being proposed for application pathology as pathology gets more and more digitized. So it's very exciting times, and we are very excited to have two very prominent speakers, Dmitry Nechaev. He is the chief AI scientist at HistAI, and then my dear friend, Dr. Rama Gullapalli. He's a physician scientist, associate professor in Department of Pathology, joining us from University of New Mexico. So with that, I'm going to turn it over to Dmitry to talk about the exciting work that HistAI has done about developing these foundation models. And thank you for making them available to a lot of us.
Yeah, thank you. Let me share my screen. Okay, is everything good?
Yeah.
So yeah, welcome everyone. Thank you. I'm Dmitry Nechaev, Chief AI Scientist at HistAI. Recently, we've trained a family of foundational vision transformers for digital pathology called Hibou. And today I'll discuss why and what can we achieve with them. Plan for today is first I'll talk about origins of vision transformers, and I'll talk about modern methods of their training. Then I'll talk how we train our models and which applications are available for them. So vision transformers are advanced deep learning models that are designed for image analysis, and they leverage the transformer architecture that is what was originally developed for natural language processing. The concept of transformers originated from the famous paper, Attention is All You Need, and this architecture was adapted for vision tasks in the paper, An Image is Worth 16 by 16 Words. So it's a diagram from the original paper on vision transformer. The authors of this paper, their goal was to adapt transformer architecture to vision tasks with as little modification as possible. So they basically only modified the data input and how it is prepared. So instead of the text that is embedded, it's an image. An image is sliced into smaller patches. In the original work, it's 16 by 16 pixels patches, and then these patches are linearly projected, and we also add positional embeddings to them, and we add one more class token. Then this sequence goes through the transformer, and we attach an MLP head on top of the class token, and we can predict the class of the image. And the transformer encoder, it features like the default transformer block architecture with multi-headed self-attention and linear layers. So what are the advantages of vision transformers? The greatest advantage and simultaneously disadvantage is their scalability. They efficiently scale with larger data sets and more computational resources. They can handle more data effectively, and they improve the performance with getting larger. But on the other hand, they perform poorly when trained on smaller data sets, as I'll show later. Vision transformers are versatile. They can be applicable to multiple vision tasks, like classification, detection, segmentation, and so on. And in comparison with convolutional neural networks, the attention mechanism in transformer models allows them to better handle long-range dependencies in images, which offers a global perspective on input images. And transformers scale better than CNNs. But as I already said, they are not that good when trained on smaller data sets. This is a plot from the original paper as well. Here, the authors compare vision transformers to state-of-the-art convolutional neural network at the time. BIT, it's a big transfer, not transformer. And here we can see, like in this shaded area, it's performance of convolutional neural networks. And when trained only on one small, relatively small data set ImageNet, transformers basically lose. And also, interestingly enough, the strongest transformer model is a base model, which isn't that large. Then when we train on ImageNet 21K, which features 40 million images, we get stronger performances comparable to residual networks. And Vision Transformer large version is the strongest among transformers. And when we train on 300 million image dataset, we get that the biggest model, Vision Transformer Huge, is the winner. So in modern days, vision transformers are the best at basically all the main vision tasks. These are the screenshots from papers with code site I took. And we can see that on classification, detection, segmentation, all of the models that are ranked on first place, all of these are vision transformer architectures. So that's why we want to use vision transformers for our tasks. Now let's talk a bit about what is a digital pathology. We'll come back to transformers in a minute. So pathology is the study of disease tissue under a microscope, which plays a crucial role in medical diagnosis. It's the standard for diagnosing various conditions, particularly cancers, by identifying cellular abnormalities and changes in tissue. Traditional pathology methods involve staining tissue samples and then examining them manually under a microscope. In recent years, there has been a significant shift from traditional pathology to digital pathology. Digital pathology involves scanning conventional glass slides to produce high-resolution digital images, known as whole slide images. These images then can be analyzed using computer algorithms. And it's how the whole slide image is prepared. So first we collect the tissue, then we process it by dehydrating it and then clearing. Then we place the tissue into a mold and fill it with the paraffin. And once it's solidified, we slice this paraffin block into thin sections. Then we do staining process. The most common staining is HND. But there are some other special stains that are used for other use cases. And then we scan this using a high-resolution scanner. We scan these small tissue samples at high magnification, like 20 or 40 times. And the resulting whole slide images are very high resolution, up to 100,000 by 100,000 pixels, or maybe more. And this is the result of this process. It's how whole slide image looks. And this is then later used by pathologists to perform the tasks to diagnose patients. So why did we train Hibou? Vision transformers that are public, they're trained on natural images that are very different from pathological images. And because of that, generalization suffers. So they don't perform on pathology-specific tasks as well. And we also know that when trained on specialized datasets, vision transformers show stronger performance in the main tasks. So we need a large specialized dataset, and at HistAI we've acquired a private 1.1 million whole slide image dataset. But the problem is, how do we train the model? Because as I've shown earlier in the first work, they just trained a classification. They trained the models on the classification tasks, but we don't have labels for patch level images. Basically, we have very huge slides, but we can't directly input them into transformers because they're very large. So we slice them into smaller patches, but we don't have any information about the patch except the patch itself. So let's review what are the methods for training vision transformers, and which one did we take. Yeah, so the easiest one is a supervised learning. We just use a label dataset and train the vision transformer to predict labels from images. But this approach requires class labels. Also, one very prominent approach in the modern times is vision language contrastive learning. An example would be a clip model, which is it was trained by OpenAI using a contrastive learning between images and text descriptions. Basically, in the process of vision language contrastive learning, the model learns to sort of map text descriptions of the image to the image itself. The text encoder is used like BERT, and vision encoder is used like a vision transformer, and we produce some features, and these feature vectors are pushed to be closer together to sort of show that they represent the same concept. But this approach also can be used by us because it requires image text pairs, and we don't have text descriptions for the patches. And this brings me to the third very popular method used for training transformer models nowadays. It's self-supervised learning. It doesn't require any labels, and it's good for training on large-scale data sets. So it's perfect for our use case. And among many methods that were developed, the recent and the best currently is DynaV2. So we used this method, and let's review it to better understand how self-supervised learning works. Yeah, so the method was introduced by MetaAI Research. It's a self-supervised method where the model itself is the teacher and the student. It is achieved by a very simple trick. The teacher model is a moving average of a student model. And DynaV2 is a combination of the original Dyna and iBot methods. So let's review these two approaches. They both include having a moving average teacher, and they're quite similar in what they try to achieve, so they can be paired quite effectively. Let's start on the right. It's an iBot method. How does it work? First, we have our image that is sliced into smaller patches. We actually generate two different views of the same image. It's basically they're generated using different sets of augmentations like color jitter or blurring, something like that. And then the teacher model gets as input the full image. And the student model, it gets only some parts of the image, and other parts are masked. So it doesn't see the whole image. And the task for the student model is to predict for these missing parts that were not provided to the model. The task is to predict what the teacher model would output for these missing parts, and the teacher model, as I said earlier, it can see the whole image. So the teacher model outputs patch tokens and then the CLS token, classification token. These go through heads specialized, and then using masked image modeling loss, the student model tries to predict what would a teacher model output. And also why we need two images, because classification tokens are also predicted, but in this case, they are predicted for like the first a classification token for the first image is predicted from the second, and vice versa. It is needed to add more generalizability and sort of invariance to possible variations in images. As I said earlier, these two images are the same image, but they are augmented, so they look not exactly the same. And then there is a Dino framework. It doesn't require masking anything, but it also shares the same idea of trying to predict the output of a teacher model that sees the whole image by showing only part of the image. In this case, student model gets only a small part of the image, of the original image, and it's also augmented. Basically gets a local image, local part of the image. Then it predicts a class token, and it tries to match its prediction to the teacher model. And in this diagram, there are only two views, but in practice, there are actually more local images used, around like 6 or 8. And in combination, these two approaches, they are combined into Dyna V2 by basically this method achieves that the classification token learns a lot of invariance to various changes in the input image, and the patch tokens, they learn to be to sort of pay attention to the rest of the image. So what did we do for Hibou? We modified Dyna V2, we slightly modified Dyna V2 to train our models. We included a pathology-specific augmentation called Renstain NA. This augmentation, it simulates variations in the staining process, which occurs all the time. So it's very useful to learn to be invariant to small changes in stain. And also we added other useful geometric augmentations like random rotations. They are not default in the Dyna V2 for natural images. We will also optimize the image loading by storing tiles in CWDFS. It's a specialized fast distributed storage system. It is optimized for large quantities of small files. Our full data set consists of tutorial 1.1 million HND slides, but it's not only not HND, just whole flight images, and they are mostly HND slides. There are also non-HND stains, which is quite important to have as much variation in the training data as possible. To prepare clean tiles, we use the following approach. We just find the tissue using auto thresholding, and then we split a slide into non-overlapping tiles and take tiles that have at least 20% of tissue. We've experimented with more sophisticated approaches, like having a specialized quality control model or using some clustering methods, unsupervised clustering methods, but they've proven to be like they didn't actually bring any advantages, or maybe they even resulted in a bit poorer performance. So, and they are computationally expensive. So we stick to a simple auto thresholding. And some features of our models. We have two, Hibou large and Hibou base. Hibou large is 300 million parameters, and it was trained on 1.2 billion clean tiles. It was trained on 32 A100 GPUs. And Hibou base, it has 86 million parameters, quite smaller, and it was trained only on 500 million clean tiles using only 8 A100 GPUs. But this model is publicly available with Apache 2.0 license, so everybody can try it. This is also a diagram of distribution of various tissues and stains in our data set. It consists of a lot of different tissues and not so different stains. Mostly it's HND, but it's still quite a lot of other stains. These are the results from the paper. So the top table shows a patch level evaluation. Basically, we have some data sets that are labeled, and they have patch level labels, so we don't deal with the whole slide image. And to evaluate the models, we train only one linear model atop of the classification token. That is an output of transformer models. And then we test how good the model, sort of in the simplest possible approach with only one linear layer, how much better can we, what can we achieve with that on a specific data set. And Hibou large achieves quite good results on most of the data sets, and it's best on average for patch level tasks. Then for the bottom table, it shows slide level benchmarks. To use this model for slide level, we need to first we also cut slice the whole slide into smaller patches, and then each of patch is embedded into like feature space using vision transformer. Then we use another model on. Let me actually illustrate how it looks. So we split the whole slide image into patches. or they go for a feature extractor, we get a sequence of patch embeddings. Then we have another model, but it is way, way, way smaller than the original feature extractor, so it's really fast to train, and it doesn't require a lot of extra data, so it trains well on small data sets, and it's trained to predict diagnosis. And these data sets, they are publicly available. These are different data sets from TCGA. And Hibou also shows the large model shows the best performance on them compared to another model that is actually even larger, GigaPath. Let's check some real-world examples, how all of this works in real life. We at HistAI have developed a platform called CellDX. It's an online whole slide image viewer embedded with cutting-edge AI technology. It allows pathologists to examine digital slides and add their own comments or maybe annotations. It works very fast, like allows to see on cell level or a very sort of general overview of the slide. And we have quite a few models in there. Like, for example, on this slide, there are actually a lot of models that are used to generate a prediction. But first, we take the slide and features are extracted using Hibou. And then we use smaller models to predict diagnosis or segment tumor tissue. So in the chat, we can see that it predicts that it's a melanoma. It predicts that there is no ulceration. So each of these predictions is a different model, but it's a small model trained on a relatively small data set. And it never sees the slide like images themselves. It is trained on features that are extracted by Hibou, and in turn, we don't need to retrain our model, fine-tune it for specific data sets. It works very great out of the box. So yeah, we get predictions using classification models that has architecture like on a previous slide. And also we use another model to segment the tumor tissue. Once again, we use Hibou features, and then there are extra modules to support segmentation. We have annotated manually some slides with tumors and trained model to predict tumor masks. And then we use just classic computer vision algorithms to calculate the depth of the tumor. There are a couple more examples. I won't go into much detail. They basically all follow the same principle. We use Hibou to extract features, and then we use a smaller model trained on a specific task to perform that task. Like, for example, we can find an epidermis and then calculate its thickness, or we can say predict that on this slide is a different type of cancer, basal cell carcinoma, and use a different segmentation model to segment the tumor itself. So thank you. Some useful links is a platform if you want to try it, cellDX.his.ai. And also the base model is freely accessible to everybody. You can check it either on Hugging Face site or at GitHub. I think I can post these links in the chat if anyone interested, once again, thank you.
Thank you, Dmitry. That was very exciting. If you can leave that slide over there so that people can look at those. And I did put in many of those in the chat too. And that's great. So this is very exciting. I was listening to how you built it, and there are so many questions both in the chat and that come to my mind. And we have Dr. Rama Gullapalli. He's a pathologist. And I wanted him also to join us to give us a user experience, because at the end of the day, the pathologists are the ones who stand to benefit from this, other than our patients. So Rama, I'm gonna turn it over to you. I do have a few questions myself too, but I'll let you moderate this from here. So thank you, Dmitry, for the excellent presentation here.
Thank you.
Thank you, Piyush. That was a very interesting presentation for sure. And I'm coming from the perspective of an end user who would be interested in these technologies and the way it would impact our field of pathology. But I also just saw that there is an absolute expert in the field of pathology, Dr. Raj Singh, who is a dermatopathologist and actually the founder and CEO of Path Presenter, a globally used software platform for pathologists. Dr. Singh and I have collaborated on multiple things, and I was delighted to see him join in this presentation. I would like to invite him to join also the conversation of this QA if he's amenable to that. But however, let's start with the questions we have in the chat. So we have a question from, okay, sorry, I'm trying to find this. Okay, from Zolt Bedozi, who says, how do you determine the tissue content of a tile to keep only those that contain a minimal of 20% of tissue? So that's his first question.
Yeah, I've briefly mentioned it. In training, we use the simplest possible approach. It's just an auto thresholding. It outputs a binary mask.
Okay.
And since we have like a white background, it's very easy. But actually on CellDX, we've trained another lightweight model to determine tissue like more precisely, and also to not include maybe potential slight, slight damages or something. Like there may be impurities that would be included if we just use auto thresholding. But for CellDX, we use another segmentation model that just segments only the tissue. And then we take patches with the tissue to feed into the classification model.
Okay. So a question from Santosh says about the training. How long did the training of the Hibou B and Hibou L models take?
So the large model, I think it took actually a month, so it was a very long time. And a base model, it was quite fast, in around a week or 10 days, something like that.
Okay, so not too long. So is this because of the computational A100 cards that you guys were using?
We've used, A100 cards were used for both large and base, but as you can see, I don't know where I said it. We used only 800s for base model and 32 for large. And well, large model was trained twice as long, just in terms of, even more than twice as long in terms of the amount of tiles used. And because it's larger and we need to train it for longer. And it's also, it in itself, almost 4 times larger in terms of parameters. So it requires a lot of more compute, which all adds to, even when we use more GPUs, we still need to train it for way longer.
Zolt has another question. For slide level classification, the transformer encoder received bag of embeddings with a different size. So he's asking, how was this handled, and did you pad the input if needed?
Yeah, if we are talking about this part, just in case, I'll clarify that the Hibou model always receives the same amount of patches. It works on 224 by 224 images, and its sequence length is always constant. But for the classification, for the sequence classification, yeah, this sequence it already, like, it depends on the size of the slide, and when we train this classifier, yeah, we just pad this sequence with like something and mask these tokens, so they are not seen by the classifier model. And in production, like, it handles pretty well different lengths of this sequence. If we predict only on one slide at the time, we don't need to pad anything. But the model itself, it is like, it works good for different sequence lengths.
Okay. So Piyush, you said you had a few questions. Do you want to go ahead and ask?
Yeah, I always wonder, like, because we look at the performance of a lot of these models, and we use a lot of technical benchmarks for evaluation. But then when you look at the human evaluation part of it or expert evaluation part of it, many times we find a gap because the technical evaluations are measuring certain parameters, whereas there is sometimes a gap in what the human values are and the need over there. So to give you an example, like in radiology, it's very common to see these models which are trying to predict, 12 different disease states or so, like a pneumonia looking at an X-ray or pulmonary edema or something. Whereas when you're looking at human evaluation, you either find that that is not as good, the performance is not as good, or what you're expecting is sometimes even multiple classes that you need to predict. So in Dmitry, in your opinion, or Rama, in your opinion, like, how good are these benchmarks and evaluations when you compare them and what the pathologist truly needs? Because pathologists, I'm sure, are looking at many different things when they are trying to use the output over here.
Yeah. I'll let Dmitry answer first, and then I'll offer my thought. Go ahead, Dmitry.
Yeah, well, I come from technical background, not pathological background, so I guess my answer won't be won't be very broad, but we at HistAI, we sometimes we have our, like, pathologists who work with us. They help us to annotate the images to later train our models. And so we sometimes basically just ask them, what do you as a pathologist want to see? And basically try to go from that. But also we need to, use some common benchmarks that everybody is using for, like, standardization of evaluation of our models. And I guess they should be correlated, but I'm not sure that it's like an exact correlation.
Yeah. So as a pathologist who kind of has a feel for the things in the AI world, I will say that the evaluation component of many of these models is kind of lagging in a sense. Most of the times you see a lot of these papers, publications use a standard benchmark set for the evaluation, and the outputs are determined in terms of accuracies crossing 95, 96. But that doesn't translate one-on-one to the real life scenario. There is a lot more in terms of evaluation accuracies that need to be measured, in the way they are measured, the standards. So, getting a large enough test set to evaluate and put out a publication, I think is a much, much lesser threshold compared to translating it into the real world. Now, exactly how we go about that, I think that's still a work that needs to be done. But I would say the real world translation is way different than a test or training data set based evaluation. So Dr. Singh asks, how do you see this evolving as most models are using specific tiles that are quite small in size? So you use the 224 by 224 patch size. So Dr. Singh is asking, how will GPUs be able to handle data such as WSIs, which are much, much larger? Do you think that's going to be a problem? So a scaling question. So you're training on 224 by 224 patches. Do you think will that scale well enough to WSIs, which are much larger as well?
Well, to be able to use the transformer model, like feature extraction on a whole slide at once, like skipping the part with extracting smaller patches and then using them for later tasks. It isn't very easy. It's basically sort of impossible with the current implementation of a transformer of vision transformers, because the attention in them scales quadratically, which is like it would blow up really fast. But there are some attempts in the field to basically use another attention implementations that are not, they lose a bit because they can be global. They can't attend everything to everything, but like Microsoft is developing their own approach with LongNet model, which uses local attention. It's actually somewhat similar to convolutional neural networks, and it handles larger sequences pretty well. But currently, how we do it is we don't extract features from the whole slide all at once. It's split in batches, and then we extract features using like in batches and then when we get features, and these are actually already really small, so GPUs can handle them quite well, even not so modern, like V100s or something.
Okay. So Dr. Singh has two more follow-up questions, which I also have. I'll ask them from a modified perspective. So the trend seems to be in pathology foundation models going towards smaller sized models with smaller parameters. In your own paper and a recent paper that was comparing, that was put out by the folks from Page, showed that smaller sized parameter models seem to be doing as well as larger sized models. So what is your take on that? Do you think we will go towards getting more smaller sized parameter models, or do we need larger sized parameter models?
I think it depends on the task, and basically, if we compare our models, the base sort of loses to large, but not that much on average. Yeah, and it also can be improved. I think if you like there is one approach called distillation. If we first train large model and then we use that large model as a teacher in Dynavi2 for the base model, not the base model itself, then we can increase its quality even more. Maybe we will do it in the future. But I guess there are smaller models. I don't think they can actually outperform larger models when trained sufficiently, when larger models train sufficiently. So it's like a question, do we really need like a couple more points? But then we need to use way more GPU and like in general, it gets slower and more expensive.
Interesting. So that follows the next question. Dr. Singh asks, what kind of infrastructure will be needed by institution and the costs involved? I also have an addition to that question. Who is your target audience in terms of the product that you're offering? Are you looking to institutions? Are you looking to other companies, individuals? Who are you targeting?
Yeah, in terms of infrastructure, the base model doesn't really require that much. You'll be good with one GPU, even not 800, even consumer grade GPU. If you want to train something yourself. But in terms of CellDX, we handle all the training and inference, so you basically don't need anything if you try to use it. And about our target audience, it's institutions or potentially like CRMs that perform some extra work, outsourced work. So like our goal is to sort of help them do it faster, assist in it, not completely replace them.
Okay.
Yes.
Okay. So there was another question about, sorry, pull this up. Why don't we try multiple instance learning backed by CNN's base structure? So basically, I guess the question was, what significant improvement do VITs offer or multiple instance learning using CNNs?
Yeah. Well, we use multiple instance learning as well, but we use transformers over CNNs. Basically, transformers are just stronger at anything nowadays.
Correct.
So yeah, that's it.
Yeah. So one more question. Is there a quantized version of the B model available?
When you use the base model, it's stored in FP32. So it's not quantized, but in PyTorch it's quite easy to run it in FP16, floating point 16. So it's sort of automatically quantized by PyTorch if you're like, I don't know, check online how to do it. And about potentially quantizing it more, we actually didn't think about it because, to be honest, it's already quite fast and not that large in terms of memory. And in my experience, when you quantize it more, you don't really get that it much faster. You get the model smaller, but I'm not sure if you really need to get it small.
Okay. So Ramanathan is curious about what are the next steps to get these models involved in day-to-day patient care, at least from your perspective. How can we get this into the clinical practice? What are you guys at HistAI thinking about?
Yeah, I think it's like we can maybe a sort of top-down and bottom-up approaches. like used. We can maybe potentially a pathologist sees a CellDX, tries it for themselves, and they see it's like quite convenient. So they might sort of ask, is it possible to incorporate? But I guess more efficient approach would be to have some direct deals with businesses, like a B2B approach, because it's like easily quantifiable. In the sense that we say that we will speed up your process and like enhance your accuracy. It's like you try it. If it did really speed up, then you're satisfied and you ask for more.
Yeah. I'll take the moderator's privilege and ask one last question to close this out. Are you able to say what is the non-H&E slides that you were using your training for? Was it immunohistochemical stains?
I don't remember exactly. I know there are IHC slides.
Okay.
Yeah, and I guess something else, but I don't remember exactly.
Okay. All right. Thank you, Dmitry. That was a wonderful presentation. Really enjoyed it. And I will hand this over to Piyush.
Yeah, thank you, Dmitry, and thank you, Rama. Again, I'm not a pathologist, but I was listening to the conversation. What it tells me is the depth of expertise that Dmitry brings in. Thank you for being such a sport and answering all the questions so well. I learned a whole lot from this, and I think there is a great opportunity to get your work to implementation to help our pathologists, to help our patients, and that's what we are trying to figure out and looking forward to. And it also tells me the expertise that HistAI brings in to this, from all the questions that you answered and the presentation that you gave and the work that you have done, it just shows how deep the expertise is over there. So I hope many others will reach out to you to leverage your expertise to the wonderful work that you have done. We all learned a lot. This recording will be available through our YouTube channel. And I appreciate all the members who joined us today for this exciting session. And thank you, Rama, again for the excellent moderation. So until next time, please follow us on BrainX Community on your favorite medium. Thank you, everyone, for joining us.